Assalamu alaikum and hello everyone. We are Team Green Card and this is our project for the course Digital Electronics. In this video, Ahnaf Monnaf Mashuk and I, Muhammad Rafiduzzaman, will be presenting our digital snake and ladder game. We will walk you through the different modules of our project, explaining their functions and how they interact. Finally, we will show a full gameplay demonstration to see everything in action. Let's get started. Our project is a digital implementation of the classic snake and ladder game. It consists of multiple modules like the dice module, snake ladder logic, game memory, player selector and winner module, pair position decoders, board module, ladder and snake position decoder, etc., and the integration of these components. The goal is to simulate the gameplay using digital logic circuits.
This is the dice module of the snake ladder project where it will give the output of the dice value within the range of 1 to 3 that will be used to add and determine the player's next position according to its logic. Now, the way it works is we have used a Johnson counter. It will tell us it will take a high signal of each pin from Q0 to Q9 based on the clock pulse that is given in this circuit, and this MR pin is used to determine the reset option where the signals will reset from its starting position. So to give the clock pulse, we used a stable multi-vibrator in the dice pulse section. If this is a stable 555 type of stable multi-vibrator, it will give the was state 1 and 0 simultaneously side by side to give a clock pulse generator for the our entire snake ladder project. And here we used a edge triggering that will give only a positive trigger after we take out our dice button that will be used in the memory module. Here, the resistor and capacitor are there to determine the frequency of this multi vibrator and the clock pulse side by side, and we take the clock pulse output from this AND gate. Now, the way dice module works is from Q0 to Q2, it will give one high signal simultaneously, just like one, then one, then one. So it's like a process. Now, if we just connect these three input to the BCD 7 segment decoder, that there's a problem because the first thing that give the high signal is Q0, that will be showed in 1. Then second will 2. But when it comes to 3, the Q if Q2 gives a high input signal and the other two remains low, then it becomes 4 instead of 3. So that's why we used XOR gate to determine the 3. The way it works that we take two inputs from for each of the circuits input from Q2, and the other inputs are taken from Q0 and Q1. So when it reaches Q1 high signal, that is when to each of the circuits one input. And there's a particular property of circuit is that if one of the input is 1, then the other inputs will flip. That is, if there's the other input is 0, the output will be 1. So that's how we use this technique to maintain to give the output 3 in our BCD 7 segment display. The way it works is when it reaches Q2, then the XOR gets one input is 1 and 1, and the other two inputs is 0 as well as 0. So that's why the output is became 1 1, because due to input high signal of each of the input for the XOR gate, the other input becomes flipped. So it was 0, then it became 1. So 1 1 means our binary 1 1 means our decimal 3 that is shown in the BCD segment display. And here we use IC7447 to decode our BCD value to its 7 segment value. And if we just show you the module, then we add a dice button here to power up the entire module. That will be with a push button. So if we take push one of the input, then the dice will continuously changing, and if we take it out, then there is a particular value that is added to our board module, and this value goes to other modules as well. And so that's how the dice module works. To demonstrate the dice module with lower frequency, we can change this capacitor right here to a lower value that will change the frequency. Initially, it is set on 0.1 microfarad, but if we change this into, let's say, 5 microfarad, so this will change the frequency of this dice clock. And as you can see, if I run this project and play the dice button, it will slow down the pseudo random numbers that was generating so fast. Now it's generating so slow. In this way, you can actually see the actual function of our snake head and tail, and let us start and end by placing our players there. Initially, our snake head and its tail are placed at position 9 and 2, and let us start and let us end is placed at position 4 and 13, and our players are initially at position 0. So if we start this game right now, so that first player rates turn. So let's see. So we need number 1 dice from the dice value to see the ladder working for the red player. So let's see here. the red player went straight up from 4 to 13. And now to see the functionality of blue player for the snake, we have to make the dice value as if the blue player will fall into position 9. Let's see how it goes. So see, whenever the blue player falls into position 9, he immediately gets down to position 2 because that's the snake head and that's the snake tail, and that's how we know the function of snake and ladder are working with the dice value slowing down, so that we do not miss the steps. And to win a player, we need a value of 2 to for the red player to win. So this red player's turn, and if we just generate the number 2, it won and the buzzer is started playing. So that's how we know the functionality of the board of this entire module, with the dice module being slowed down to show the real-time update of it.
The board module displays a 4x4 LED grid representing the game board. Each block corresponds to a position on the board starting from 0 up to position 15. The red LEDs indicate the player 1, blue LEDs are for player 2, yellow LEDs are for the snake position, and the green LEDs are for the ladder position. The LEDs are in active low configuration, meaning they turn on when receiving a low logic signal. To prevent damage to the LEDs, current limiting resistors are used.
This is the part where we explain snake ladder logic, the heart of the entire project, and the way it works. That if we go into the child sheet of this logic, and we can see there's a dice adder, there's a ladder position comparator, and there's a snake position comparator. So I'll be explaining the logic behind it. Basically, if we get the dice value from the dice module, it basically adds and there's current position from the board module, and this will add to make the new current position for the selected player. But there's so much factor to deal with. If there is a ladder or there's a snake and there's no ladder or snake, or if both ladder end and snakes, if both ladder and snake at the same position, then what will this logic do? So firstly, we can discuss the ladder position comparator. Basically, if there's any ladder end at any given position, then logically that player should go up to the ladder end position. So the way it works, that it takes input from the dice adder result that is given right here, and compares with the ladder start position that is taken as an output from our ladder position module, ladder set module. And then it compares if there's a match for the exact same, like if there's a ladder start at 3 and the player's position is 3, then QA is equal to QB, pin number 6 turns on, which basically turns on the entire AND gate operation of this U10D IC, where each AND gate gets input from this QA equal to B pin, and the other input is basically the ladder in position taken from the ladder position module, and it basically uh, functions the AND operation and passes down to 3, 6, 8, 11 pin number, and the other which basically passes down to this or operation, and then the other input is taken from this U9D and operation with basically 0, because there's no invalid input for this case. So it's basically the same result as before from the ladder position comparator, that is 6, 9, 6, 3, 6, 8, 11 pin. So which passes down to this position, because this position, and the other input is basically 0 because there's only ladder position and there's no snake position. So snake position, that means that this IC will give QA equal to B, 6 pin is equal to 0, which basically eliminates this AND operation and this AND operation, vice versa, because this is 1. To shut down this operation, we taken a not get input from this ladder position comparator, pin number 6, to make it 0, because if this is 1, then this entire operation will go to 0, and this exactly comes from here, and doesn't matter this input, because it's actually making 0, which results this operation to be 0. This operator to be 0, and so basically the result of this or this for or operation is basically 0 0 0 0, which makes it the sole player new position to be the adder or the adding value of player's previous position with snake ladder start position to ladder end position. That's how the player's new position is calculated for ladder position comparator. Now if there is a snake head at any given position, let's say 12, then what will it happen? Then, so basically, if there's only snake head, then automatically ladder position IC will give 0 output, which basically cancels this operation. And this operation, U90 IC operation, is already cancels because there's no invalid input. If there is any invalid input, the carry output will be 1. That's how then this U90 ICs of 4 AND gates will be activated, but there's no output as it is 0 because this valid input. So this is 0. This operation cancels out. This operation also cancels out, which basically cancels U17 IC of this 4 OR gate. Now, from the snake position comparator, this QA equal to B, which gives input 1, which basically passes down to this U11B ICs, where snake end position is given from snake end position is given from the snake position module, and the player position is also given here, which basically activates and this. So that's how a snake subtractor works, and it will give the player's position back down to the snake in position that is set by the user from the snake position module. That's how the actual value passes down to these 4 OR gates, which eventually passes down to these 4 OR gates, because we already explained that the 0 value for these 4 OR gates actually 0, and the value for these OR gates are 0. So which basically means that whatever the result will be, the result is already be here at the snake position result. That means that it will give the exact position for the calculated position for snake position comparator if there's any snake at a given position. Now, the third case is if there's no ladder or no snake, then what usually happens in this game is actually the dice adder will just forward the step by the according value that is came from the dice module and update the player's new position. That is actually works is if there's no ladder and no snake, then the output is 0, which basically cancels this position and this position, as this is a valid player's position input. Then this position or these ICs are already deactivated because of the carry 0. So these positions are already 0, and then only U13C ICs of this 4 AND gate operation will occur because we have taken output from this dice adder normally, and the other inputs are from this NOR gate, which basically gets to on because these are one of the inputs from the snake ladder position QA equal to B output, and the other one is snake position comparator for QA equal to QB output. So 0, 0, 0 into 0 is equal to 0, but as it is as NOR gate, the output value will be 1, which basically activates the 4 or AND gate operation. That means one input for each input pin for each AND gate, and the other one is the 4-bit value of dice adder result. That is the player's new position, which basically actually acts as a simple addition for player's new position if there's no snake and ladder at a given position, which basically activates this OR gate, because the output of each pin for this OR gate is basically the same as before for U13C IC, as this U11B ICs of 4 or AND gates are actually 0, because I explained it already. Because of the snake position comparator, output pin 0, there's no snake head at this given position, which basically results the output value of the entire operation to be the exact as this U13C, because there is no other valid input from this side, because this side is already be 0, as I explained earlier. So that means the solely remaining 4-bit value of this OR gate result is basically the same as the snake error position. The dice error position, where the dice adds its value with the player's current position, as gets a new position from this operation, and which basically results here. That's how the dice adder works. Now, for the last case, if there's any invalid position. Okay, so if there's any invalid position, let's say for a player to win, he needs only 2 points, as his current position is 13 and the final position 15. He needs 2 points, but the dice value gives 3. So what will be happen in that case? So in that case, the dice adder will give a carry output 1, because there's an invalid operation. There is a there's the input of beyond of our limitation, that is 1 to 3. So this will give 1 output, and the other ones are 0, obviously. So these are actually not activated. So basically, these 4 AND gates acts as an operates and gives the exact value or the player's current position, because there's no change in player's position if there's any invalid operation. That's how the snake ladder logic works. And to test that if each individual thing are working properly, we have connected probe here. And to explain snake logic and ladder logic, it actually acts same. Just there's a little bit of different. Ladder logic acts as an adder, because we basically adds player's current position to dice value, and adds to get a new position that is higher than the player's current position. That is why we use adder, and there is a carry output 0. So if both are correct equally, then we'll get a position here, and we use this 4 to 16-bit decoder to decode this value to our board module. And the way it works, because we used so many AND gates here, it's basically the LED on the board module acts as active low operation. So we need value 0 for the particular operation that is shown here. That is the at any given position. Let's say the player's position is 3. So I need value 0 for this 3 position. So how do we get that? So to get that, as if we because the way it works is if there's any position here in 4, then the other will be 1 and the 4 will be 0. So that's how we use AND gate to mitigate all the other 1 value and give the 0 value for this exact position. That's how the ladder position works. Snake position logic is exactly the same. I'm not gonna explain it again. Just there's a little bit of difference. That is, instead of adder, we use subtractor uh, by taking a value of high signal to carry input. If we get the carry input 1, then it will act as a subtractor instead of an adder. That's how snake logic works. And to test, if we test, we used logic probe here to demonstrate the 3 module that I've discussed here. If we turn on the entire project, you can see the ladder start and ladder length is given here. So basically, it will add and it will basically give two value here. That is 1 0 is for ladder start, that is 6. We get 6 0, and ladder end, that is 6. We get 12 0. That is basically logically correct because LED acts as an active low. So we get both module here for 6 and 12. Now for the exact same thing happens for snake. That is we give there is a given value, that is the snake length value. It will basically subtract and we can get the tail position of the snake, and that is expressed here in this snake ladder logic module, where we get output 0 to the LED lighten up in the board module as this LED is used as active low operation. That's how we get the snake head and snake tail position from the board module. And if we perform an experiment, if we get a value of dice, then the player position will change. That, let's see, if we get one position, see the player rate moves from 0 to 1, as this is the case where I explained there is no ladder or snake is given at this position. So that's the usual case for this to happen. If there's any snake and ladder, it will occur accordingly. That's how snake logic and ladder logic works.
The memory module stores and updates the positions of both players. It consists of two 4-bit D-type flip-flop registers that store player positions and update them based on dice rolls. The player selector module determines which player is currently active and ensures the correct position is updated. For the memory section, we have inputs that comes from the snake ladder logic, which is the current player's new position. We have current active player's current position that goes to the snake ladder logic module. We have player 2's current position, player 1's current position, an input that comes from the dice module, a player signal that comes from the player selector module, and a reset signal. Inside the game memory, we have 4 D-type flip-flops for player 1 memory, another 4 for player 2 memory. These D-type flip-flops are configured to act as registers that update the position of the players accordingly, and we receive signals from the dice and from the player selector that determines when to update which memory segment. Let's say for 0 signal, player 2's memory will be updated, and for 1 signal, the player 1's part will be updated, and we'll get the 4-bit output accordingly. If the current active player is player 2, then we'll get the output of player 2's current position that will go to the snake ladder logic. To demonstrate how the memory segment is working, um, let's say for player 1, its new position is 1010. One thing to note here is this one is the MSB and this one is the LSB. So I want to update the whatever previous position of player 1 was to this new position 1010. So what will I need? I will need a 1 signal in the clock signal of all these D-type registers. So whenever the clock signal goes from 0 to 1, this 1010 position will get passed down, and through these AND gates and the OR gates, this is acting as a demux. So whenever the player signal from the player selector module is 1, then this player 1's position will get passed down to the current player's active position output. Similarly for player 2, let's say the new position is 001. Whenever the clock signal will go from 0 to 1 and this player signal from the player selector module is 0, only then I will get the current active player position from the player 2, because at that moment, if the player signal is 0, that means player 2 is active. If it's 1, that means player 1 is active. To reset all these D flip-flops, we need a 0 signal. So whenever the reset signal is 0, all the registers will get reset, and so the game will basically start from the 0 position again for both the players. For the player selector, we have used the JK flip-flop in its toggle operation. In the clock signal, we have used the signal coming from the dice. So whenever we are pressing the dice, only then the player will get switched to the next player. Let's say it's now on player 2. If I'm pressing the dice, it switches to player 1. And for the reset signal, we have just used the signal that comes from the reset button. If I press the reset button, then the player selector will get reset and start from player 1 again. For the clock signal, there's an inverter here because from the dice button, whenever we are pressing the dice here, it switches from 1 to 0. This dice db out output switches from 1 to 0. So whenever this 1 to 0 switching happens, only then I want to update the player selector. That's why whenever we are getting 0 from the db out, only then I want to update this JK flip-flop. That's why there's an inverter here. Same thing for the reset signal. From the reset button, we are getting 0 logic output. So this JK flip-flop needs 1 to reset. That's why we have inverted the signal to get our desired output.
This is the winner selector module of the snake ladder project, and this module works using two simple IC7485, which is basically a comparator. It basically compares the player's current position with the maximum given position, that is 15, which is 1111 at the B01234. If those two numbers matches, then QA equal to P pin number 6 will give a high signal, and that high signal will lighten up this LED along with the buzzer to tell the user that this player or that player wins the game. And this is how the winner module basically works. To demonstrate how the winner module works, as you can see, the player's current position for red or player 1 is given, and for blue is given as well. And if any of the player wins the game, then the LED of the selected player, blue or red, will lighten up in the winner module along with the buzzer. Earlier that the player blue wins the game, so the buzzer for the blue player making a sound to tell the user that the blue player wins the Snake Ladder Classic Snake Ladder game. And that's how the winner module works.
The reset button or the reset module is pretty simple. We just use the push button with a debound circuit. So what happens here is when I'm pressing the button, the capacitor discharges. When I have the button released, the capacitor charges and we're getting a 1 output. In our game, we use the logic 0 as the reset signal. Whenever I'm getting 0 here, everything will get reset to the starting position. Now let's see how all the modules interact. A player will start first with the dice module. This is a dice module. A player will first generate a pseudo random number by pressing this button. So if I press this button, it will cycle from 1 to 3, and whatever output I get, 1, this 1 output will come from here and then go to the snake ladder logic. The snake ladder logic will then calculate the final position of the first player. Whichever player it was, red or blue, it will generate its final position after adding with the dice. Now if the player landed at the bottom part of a ladder, he or she will get promoted to the final part. If a player lands on the snake's head, it will get demoted to the snake's tail position. That portion is calculated by the snake ladder logic. Then it gives out a 4-bit output. This 4-bit output will go to the game memory. Whichever player was active in that player's memory, that 4-bit position will get stored. And then these 4-bit output for the two players will go to the player position decoder and get decoded to 16 outputs. These outputs go to our board module and displays the player's position accordingly. Now for this case, we got a 1 for the red player, so the red LED came here. Now let's say now it's the second player's turn, blue player. So let's say we are getting a 3. The blue will go to the third position. Then red went to the ladder's bottom position, so he got promoted to here. And then for blue, and then again red, and so on. The switching of the player is done automatically through each dice button press. The first player press the dice, it will switch to the second player, and the second player press the dice, it will switch to the first player again, and so on. Another thing that we had to do was we had to include a edge detector circuit in the memory, because when will we update the memory? It was a crucial part because everything when we connected directly, it wasn't working at first. So we had to use an edge detector in the memory, because whenever I am releasing the button, only in that moment I want to update the memory. So here we basically used a simple RC circuit. So let's see what this RC circuit is doing. So whenever I have 1 here, so whenever at first the dB output or the dB out portion would have shown a 0. So whenever the 0 switches to 1, we're getting a sharp signal output, sharp output signal. 0 to 1 sharp output, 0 to 1 sharp output. This sharp output goes to the memory. This output signal basically determines that the memory has to be updated.
This is the part where I'll be showing you the whole gameplay section of this snake ladder project. As we can see, the player's initial position is 0, but if we roll the dice through our dice module, the player position will be changed. As you can see, if I'm rolling a dice, let's say it given 1. So for the first time, the player red is forward to 1 position at position 1 because this dice value is added. For player 2, same thing happens. Then player red goes. And I would like to mention that the ladder position is connected with position 4, and the snake head position is position 9, so that if any of the player goes to position 9, he or she will be deducted to position number 2. As well as if any of the player goes to position 4, he or she will be forwarded to position number 13. Okay, so I'm continuing the game here. See, that's how the players are going. That's how the players are starting at the initial position, that is 0. That's how entire gameplay is conducted, and through this presentation, we are concluding our snake ladder project. We are Team Green Card, presentation by MD Rafiduzzaman and I, Ahnaf Monnaf Mashuk. Thank you so much.